Okay, so in this video we're going to talk about safety and electricity. So we're going to look at some of the typical dangers that there are with electricity and some potential areas where it becomes more dangerous. And we're going to look at some of the safety features we put in place to mitigate those dangers. So first we're going to talk about the structure of a typical household plug. And you can already see in here a couple of the safety features we have in place. So first of all, we've got the brown live wire. That's where the charges are at high electric potential energy. And then the blue neutral wire is where the charges are going back out into the grid at low electric potential energy. So that's where the energy is coming in, and then the low energy charges going back out. The two safety features we've got on the right hand side, we've got a fuse that we use, and we're going to talk about what that is a bit later on. But the other feature that you can see is the earth wire, the yellow and green one, and that is just a protection based wire. So it's there in case the live and the neutral short circuit, or they touch each other, metal to metal, or if the live wire touches the metal casing or something like that. So that's why the earth wire is there, and the way it does that is the earth wire is at very low potential, or a potential of 0 in fact. So if there's an issue, a short circuit, all of the high energy charges get directed down the earth wire, literally into the earth. In a socket inside your house, there'll be a wire which is literally plugged straight into the earth. So if there's any issue, all of the high energy charges go straight down there, and then there's not any issues from that. So that's our plug structure. Okay, so in terms of how plugs have changed over time, on the left-hand side is what we have, a slightly more old-fashioned plug. And you can see in the middle there's actually a screw, so you can open it up and you can see each of the 3 wires and you can change the fuse. Nowadays plugs have evolved, so usually you actually can't open them anymore, but some of them still allow you to change the fuse inside them. As to why this is, possibly some people argue it's so people can't fiddle around with them and break them. Some more cynical people might think it's part of companies wanting you to buy more stuff so you can't fix any problems if there are any. But I'll leave that up to you to make your mind up on. Okay, so what are some actual hazards that you can get from a circuit? So the first one might be insulation damage. Now, all the wires you've seen so far have been wrapped in like a rubber or a plastic material, and we call that insulation because rubber or plastic are really bad conductors of electricity. So what that's for is to stop you coming into contact with the metal live wire inside it. Because if a current of more than 0.1 amps or 100 milliamps flows through the human body, that is lethal. It disrupts the electric signals that govern your heartbeat, and it can give you send you into cardiac arrest. I should point out at this point that doesn't mean if you touch a wire with a current of 0.1 amps in it, that will kill you, because our body is much higher resistance, so we need a much higher potential difference to give this kind of current. But that's one possible risk. So in terms of when it becomes dangerous is if that insulation is damaged, because it's much more easy to come into contact with the live wire. The next problem we get is overheating. So an equation we've seen before to calculate power, P equals IV, or sometimes expressed as I squared R. If you're dealing with a resistor, this calculates the rate of transfer of electric potential energy into thermal energy. So if you have a high current, that's going to be dissipating lots of thermal energy, and the wire is going to get very hot. And the impact of that can be it melts the insulation around the wire, and you can get damaged components. Wires can start short-circuiting if they both melt the insulation, so that can be dangerous. So in terms of what that looks like, so broken insulation is often caused by overheating wires. So you can see what's happened here. The plastic has been melted and it's exposed the live wire inside, and that would be fairly hazardous. Okay, so the third real condition that might increase our level of risk is if it's damp. So the reason why is non-pure water is a conductor. What do I mean by non-pure? It's water with some ions dissolved in it, and those ions are capable of forming a current or conducting electricity. So if Water comes into contact with the live wire, that can create another circuit. So if you touch anywhere that is damp, that could connect you to the live wire, and again, it could potentially put you at risk. Okay, so those are the kind of the three areas that we might be hazardous. So how do we protect ourselves from these? So the way we prevent overheating is using a fuse, or one of the ways is using a fuse. So you can see one in a circuit diagram if you see a symbol that looks like this. It looks like a resistor, but there's a wire running through the middle of it. So the way this works is using the principles we've just discussed. So if the current increases, the thermal power increases, which means its temperature rises. So what you do is you pick a wire with a specific melting point. So if the wire reaches that temperature, it will melt and the circuit is broken. And we can change the rating of the fuse, or the current at which it will melt, by choosing different materials to make the wire out of. Okay, so we get different rating of fuses depending on how high we want the current to be. So that's one of our safety devices. And this is what a fuse looks like. There's one in pretty much any plug that you'll come across, and a lot of devices that are battery operated would have one in them as well. But this is what a fuse looks like, and you can see the wire going through the middle there. Another device we might use is a circuit breaker, and any building that you're in will certainly have several of these. So in terms of a circuit diagram, if you see this symbol, that's showing you there's a circuit breaker. So the way a circuit breaker works is inside it there's a stretched spring. And if you release that spring, it will pull open a switch and break the circuit. So that's why it's called a circuit breaker. So that's the mechanical part of it. As to how we determine when the spring is released, we'll usually have a device that measures temperature. It's quite often something like a bimetallic strip or a relay or something along those lines. So this is a way of measuring excess or too high current. So what you do is you have a bimetallic strip or a relay, the current gets too big, that releases a spring that pulls open the switch. That's generally speaking how it works. Okay, so I'm going to show you a diagram of one of these in a second so you can actually see the inside of one. And the other thing we should look at in terms of safety is actually earthing metal machinery. So if we have a motor, for instance, we would need to do this because it's spinning and there's lots of friction. So anything with moving parts can very often become charged. So if you've got a motor, something spinning, there's lots of friction, you start charging the metal case of the motor. And if the charge gets high, someone can touch it and get a nice electric shock. Okay, so that electric shock could injure someone, it would certainly hurt, or that shock could actually damage another piece of machinery that comes into contact with it. Okay, so what you do is you connect the casing to earth, as in you literally run a wire from the casing into the earth, so that as the charge is produced by friction, it discharges through that earthing wire. So first of all, circuit breakers look a little bit like this. So I encourage you to go have a look around your house. You'll find these, and these will trip if there's a surge in current going into your house or inside your house. So that's on the left. Inside here, this is the inside workings of a circuit breaker. So you can see on the left-hand side, we've got the stretched spring ready to open the switch. And on the right-hand side, you can see it. There's actually the metallic strips that will bend and break if they start heating up. So this one uses a bimetallic strip, I think. Okay, and then in terms of the earthing wires for machinery, so you've got your motor in blue, has lots of spinning parts, lots of friction, so that can end up being charged up. But what we've got is these black wires running into the earth, so those are our earthing leads. They will discharge any charge buildup. Another way of doing this actually is using alpha radiation, which you might be interested to look up. Some machinery has an alpha source, which produces positive particles, which can help remove the negative electrons that are building up. So that's another way of doing it, but this is the most typical way of reducing static charge on motors. And that finishes this video looking at safety of electricity and how we mitigate the risk.